Yeah, so W1 is equal to X1 by S. Then what does NW converge to? Were you able to uh, solve this problem?
Sir, actually, I was watching through the lectures but didn't try it. I've only just
Okay,
watched the lectures.
okay. So, uh, um, so this problem is not such a trivial problem as it looks like. Uh, the answer is kind of intuitively you can guess the answer, but to deduce why the answer is actually that needs a little bit of involved mathematics. So let's see. The answer is x by mu, x1 by mu. And why is the answer x1 by mu? On a very intuitive way, you can say this. So do you recall the weak law of large numbers? The weak law of large numbers states that uh, this random variable, so the weak law of large numbers states that this random variable uh, minus mu, and if you do this, you take the probability, and this thing is equal to is less than or equal to variance of x1 by n
Delta
delta
square.
squared.
Delta square, yes, sir.
Yes, absolutely. So essentially what it means is that as n becomes larger and larger, for a fixed choice of delta, uh, the random variable x1 plus up to xn by n, this will tend towards mu because the probability that it deviates from mu by an amount delta becomes smaller and smaller and smaller. So you have kept delta fixed, and let's say you keep delta fixed, then variance of x1 by n, this will tend to 0. So, and now this is true for any delta actually. So because it's true for any delta, the probability that x1 plus xn by n that deviates it by this thing becomes infinitesimally small. Uh, right. So to the appropriate way of basically stating this is means that have you heard of this sort of terminology? So let's say we say that a sequence of random variables uh, tends towards y in probability. Have you heard of language like this before?
So actually, I can't recall this right at this moment.
Okay, okay, sure. So I no, I mean this is just I'll explain what this means. So if you have a sequence of random variables xn, and if I say that xn tends towards y in probability, what this means is that probability uh, of xn minus y greater than 0, limit n tending to infinity, is equal to 0. That means uh, uh, that means the set or the event that xn is different from y. So let me just write it down over here. It means the event that xn is different from y has zero probability n tending to infinity. Okay. Now the weak law of large numbers basically states that this random variable tends towards mu in probability. Why? Because let's put a substitute. So let's say we write Sn equals x1 plus up to xn yn. Okay. So then the weak law of large number states that probability of Sn minus mu bigger than delta is less than equal to this, where x1 by n delta squared. Delta squared. Okay. So if we compute this thing, so if we compute limit n tending to infinity, probability of Sn minus mu bigger than 0. So that is okay. So what is, so first let's compute this. Uh, so what is probability of Sn minus mu bigger than 0? So that is equal to probability right. So essentially what we'll do is that so okay. Um, I I hope you recall the convergence of sets. So this set Sn minus mu, this event, sorry, just give me a second. The event Sn minus mu absolute value greater than 0 is equal to the union over all possible delta of Sn minus mu bigger than delta, right? So if Sn minus mu modulus is bigger than 0, it means that uh, it is bigger than delta for some delta, right? And then you take the union of all possible delta. So now if we consider this set, if we consider this set, let's call this set some uh, an. So let's an denote this set Sn minus mu modulus is bigger than 1 by n, right? So then notice that if we, so then notice that uh, A1 is contained inside A2 dot dot dot. So in general, An is contained in An plus 1. And these sets converge from below to this set, which means that An converges to this guy. Sn minus mu bigger than 0. Okay, right. So this is a property of probability. So what this means, so if you have a collection of sets which converges from below or converges from above to some other set, then they also converge in probability. So what this means is that limit. Okay, so I think what I'll do is instead of writing it as an, I'll write it as am. Right. So it means that limit m tending to infinity probability of am is equal to uh, probability of this set Sn minus mu greater than 0. Right? But now we are going to also take limits with respect to n. and not just with respect to M as well. Um, so let's first compute this probability, right? So the probability of AM is um, uh, is bounded below. So let's write it down. So probability of AM is bounded below, or sorry, bounded above by variance of x1 by um, n times m squared. Now, if we take a limit n tending to infinity, okay, I think I should define it in a slightly different way. So the way I'll define AM, so I'm going to define AM as, instead of defining it in this way, I'm going to actually define it as the limit set. So I'm going to define it as limit n tending to infinity Sn minus mu bigger than 1 by n. Okay. So then if we define it in this way, then yeah, so if we define it in this way, then probability of AM is equal to 0. And so the probability of this thing is the limit of the probability of each of these, but each of these is then equal to 0. And so the whole thing is equal to 0. So effectively, what the weak law of large numbers states is that this random variable Sn by n is equal to x1 up to xn by n. This tends to mu in probability. Okay. So from this fact, we have to show, we have to basically compute uh, NW. So essentially, I've defined W as equal to x by s, x1 by Sn. I can write this W. So I can write this NW as equal to x1 by Sn by n, right? Now notice that Sn by n will converge to mu in probability. So from from a purely intuitive way, uh, so because mu is a constant, right? Mu is a constant. And because Sn by n will converge to this constant as n tends to infinity, we can say that this random variable, so if I define, let's say Wn is equal to x1 by Sn, then this random variable Nwn will converge to x1 by mu in probability. Uh, like, do you intuitively understand why we are getting this?
Okay, sir.
Right. But this is an intuitive answer. This is not a rigorous proof. Uh, we can see a rigorous proof, how you get to this thing. Um, If you're interested, then I can try to prove this rigorously. Because this is not a rigorous proof. This is just like it doesn't guarantee. It doesn't exactly show you how you tend towards x1 by mu in probability. Um,
Sure. Okay, sir.
okay, so let's see why. Um, so yeah, so prove that NWN tends towards x1 by mu in probability. Okay. Um, so let us compute. Uh, so first, let's try to think about a set of this kind. Uh, NWN minus NWN less than A. Let's think of an event of this kind. So if we can talk about an event of this kind, uh, we can say we can deduce the entire probability uh, distribution function, the probability, yeah, the entire CDF PDF of a random variable is decided by the probability of these kinds of sets. Okay. Now, so what is NWN less than equal less than A? So this event is basically x1 by Sn by n
And
less than A. And this event is x1 less than A times Sn by n,
okay, sir.
right? So now what we can do is let's take a random variable Zn, where Zn is equal to A times Sn by n. Okay. Now notice that Sn by n tends towards mu in probability. So that implies that if I multiply both sides with A, I get Zn uh, tends towards A mu in probability. It's nothing, it's just multiplying both sides by A. Essentially the way limits work. If limit if limit if limit of fx is equal to some k, then limit of A times fx will be A times k. Uh, that's just how it is. Um, a detailed proof, you can find a detailed proof in any standard textbook. But if Sn by n tends towards mu in probability, then Zn will tend towards A mu in probability. Okay. So we are
Okay, sir.
essentially interested in computing this set x1 less than Zn. Okay. Okay. So now we describe two events, right? So let's call this event En, where En is the event that Zn minus A mu is less than delta. Okay, so I can write this event as equal to x1 minus Zn intersection En uh, union x1 less than Zn intersection En complement. So En complement is the event that uh, so En complement is the uh, Yeah, so En complement is the event that Zn minus A mu is greater than delta. Okay.
Okay, sir.
So when you are estimating the probability, we'll take the probability of this plus the probability of this, right? Um, okay. So this is equal to probability uh, probability of x1 less than Zn union. So okay, so let's write down the in terms of probability. In terms of probability probability of x1 less than Zn is equal to probability of x1 less than Zn union En plus probability of x1 less than Zn union En
Complement.
En complement. Right. Now, if we take limit n tending to infinity, then what happens is that probability of En complement tends to 0 as n tends to infinity, right? Because uh, Zn tends towards a mu in probability. So as n tends to infinity, the probability that I deviate by any amount greater than 0, in this case delta is bigger than 0, is is 0. So as n tends to infinity, the term on this term actually tends towards 0. So if we take limit n tending to infinity, so if limit n tends to infinity, probability of x1 less than Zn is equal to uh, probability of x1 less than Zn and the fact that En. So En will now happen. Yeah, so essentially En happens uh, infinitely often over here. Um, so union En. So what is union En mean? Union, sorry, intersection En. So intersection En means that um, that Zn is between a mu. So let's just rephrase En. So En is the event that Zn is between delta plus a mu and between um, a mu minus delta, right? Okay. So the probability, uh, so the probability that this happens, the probability that x1 is less than Zn intersection En is the probability that x1 is less than Zn intersection with this event. That Zn is between a mu plus delta and a mu minus delta, right? Now, this probability is um, is upper bounded by probability of x1 less than a mu plus delta intersection this thing, which I'm going to just write as En, and this is lower bounded by probability of x1 less than a mu minus delta intersection En. Okay, so limit n tending to infinity, we have so whatever this limit n tends to infinity is, this is upper bounded by this and lower bounded by this, right? Now notice also that so if I just talk about this probability, that probability of um, right. Uh, okay, right. So this is a just stating a very small lemma over here. So let's just state a small lemma. Lemma. Let's write a lemma. So uh, let Bn be a sequence of sets. And when I mean a sequence of sets, I mean a sequence uh, of measurable sets. The sets belong to the sigma algebra on which the whole probability space is defined. Uh, such that um, probability n tending to infinity Bn is equal to 1. Then if you have any set A for any set C, you can write probability of C as equal to probability of C union Bn plus probability of C union Bn complement. Now you can take, so because the left hand side is independent of n, but the right hand side is dependent on n. So sorry, the left hand side is independent of n. That means the right hand side must also be independent of n. So in particular, you can take limits. You can take limits n tending to infinity. Now, if you take limits n tending to infinity, uh, so it means that uh, probability of C is equal to limit n tending to infinity probability of C intersection Bn. And what happens to this term? This term drops to 0. Okay. So what do we have over here? We have over here uh, a term like this, which is limit n tending to infinity, probability of x1 less than a mu plus delta intersection En. Now notice that as n tends to infinity, the set uh, the collection of sets En become probability 1. And that is just a result of the weak law of large numbers. The weak law of large numbers states that uh, from the weak law of large numbers, we have that Zn converges to a mu in probability. So the sequence of these events En will eventually, as n tends to infinity, will have probability 1. So by this last lemma, this limit n tending to infinity probability of C intersection Bn is equal to probability of C, right? So I can do is this thing is actually equal to probability of x1 less than a mu plus delta. Okay. Similarly, the term that you have over here, this let me write it again. Similarly, right. Actually, you don't need even this term. I think we can just prove it from here. So this thing is upper bounded by probability of x1 less than equal to a mu plus delta, right? Now delta is a variational parameter. You can vary delta as well, right? So in particular, this is true for any delta, right? So in particular, it's going to be true. Um, right. Yeah. I mean, you just use the uh, yeah. I mean, you can just use. I mean, it's like a sandwich theorem. Let's see why. So it is upper bounded by this term. It is lower bounded by this term. Limit n tending to infinity. Probability of x1 less than a mu minus delta intersection En. And by again this small result, this is just equal to probability of x1 less than a mu minus delta. So the term over here is uh, uh, is upper bounded by this. So let me just write it again. So essentially what this means is that limit n tending to infinity probability of x uh, less than Zn is upper bounded by probability of x1 less than a mu plus delta and lower bounded by probability of x1 less than a mu minus delta, right? Now the terms on the right and on the left are uh, uh, are dependent on delta. But this term is not dependent on delta. This term is only dependent on a and mu. It's not dependent on delta. So in particular, uh, we can take limit delta tending to 0. So if we take a limit delta tending to 0, we get that this term or this probability limit n tending to infinity, probability of x minus zn is actually equal to probability of x1 less than a mu. But what was this? But what is the term on the left? The term on the left is nothing but equal to so what is probability of x1 less than zn? Um, yeah, so probability of x1 less than zn, the way we have just defined it, is the probability. So this is just the probability limit n tend to infinity, probability of nw less than a. And that is equal to probability of x1 less than a mu. And that is the probability that x1 by mu is less than a. So what this means now, so what this means is that for each a, we see that nw as n tends to infinity is equal to probability of x1 minus u less than a. Okay, so this is just a well-known result that if you have two random variables whose uh, whose CDFs are identical. So essentially what this means is that the CDF of NW and the CDF of x1 by mu are identical. So then x is equal to y almost everywhere. Okay. Uh, so so in fact this is how we can show that this random variable um, NW or rather NWN actually, NWN will converge to x1 by mu uh, in probability almost everywhere. And that is the end of the proof. Are you satisfied?
Yes, sir.
Do you have any questions? If you have any questions, I would urge you to ask me.
No, sir.
Okay, so it's all clear, right?
Yes, sir.
Okay. So let's move on to the other problems. I think this is a good problem. This is definitely a good problem. Uh, it's a it's a good brush up on measure theory. I mean, for me, it's been a long time since I've done measure theory. So I mean, it's like a good brush up for me as well when I see a problem like this. Um, okay, so let's move on to second problem. The rest of problems are actually very easy. Okay. So we have X and Y are two independent random variables. Um, what is variance of X minus Y?
So it will be variance of x plus variance of y,
Yeah, absolutely. So
because
variance of X.
variance is
Yeah.
linear.
Yes. Yes. Absolutely. Yeah. This comes from the linearity of variance.
Yes, sir.
Okay. Uh, let's move on to the next problem. Yeah. What is the answer to this? Anyone? So you have S is again x1 plus xn, and you have binary um, random variables. Um, and you have to say which of these are actually correct. So A and B are both correct in this problem. So the first one just follows from um, the Chernoff bound. So this is from the Chernoff bound. Here in the Chernoff bound, you need to set delta equals half. And the second one is the Markov's inequality. Markov model. Okay, it's a simple problem. Okay. Let's look at one more problem. Then we can wrap up. Yeah. So so x is a Poisson random variable with parameter alpha. So what is the expectation of variance of x? So the expectation of variance of x is both alpha and alpha. So it's a well-known property of Poisson random variables that its expectation and variance comes out to be equal. Okay. So it's just one thing to keep in mind about the Poisson random variable. Um, I mean, you can look at a proof online. It's not uh, it's very easy to find. So the Poisson random variable has this property that its expectation and variance comes out to be equal, and that has some useful applications, which makes the Poisson. So that's all I have. Um, I will wrap up if there are no more questions.
Good evening, sir. Excuse me.
Yeah.
Where we get these notes, sir?
Which notes?
These this notes actually. This class notes.
Notes means the one I'm sharing in the tutorial.
Yeah, yeah.
Okay, so I am uploading the videos on YouTube. So there is a so I can give you the link to the channel.
Okay, sir. Okay, thank you.
Just give me a second.
Okay.
So I will create a playlist and I will. Uh, so the first two lecture videos are here. Um, so this is for week 1 and this is week 2. So I'll create a playlist, but just keep these videos. So this is one is for week 1, the other is for week 2. I will upload the videos for week 3 and today's, which is week 4. You can just keep following the channel and I'll be uploading the tutorial sessions. Okay. All right. So if there are no more questions, let's wrap up today. Thank you.